A simple tuning fork is shown here, and we are striking this on one of the tines. These are the two tines of the tuning fork, and it's an ideal tuning fork. We want to see how we can use Laplace transform to solve for the oscillation equation of this tine of the tuning fork going back and forth. So imagine what happens is as if I have a force applied. Uh, Imagine what happens is, for example, I apply force like this, and assuming that I am not overbending the tine, or assuming that I'm not breaking the tuning fork and the displacement is reasonably small, then what happens is, neglecting the air resistance and all the other non-idealities, then the expectation is this tine will start oscillating around the steady state point, and assuming there is no resistance, this oscillation would go on forever. So we want to find out that the oscillatory behavior, which is expected to be defined and commanded by a sinusoidal equation. Okay, so what happens is, when you apply force like this, a displacement force like this for the tine, you apply force that, according to Hooke's law, so there is this famous Hooke's law that defines that it is a very good approximation that the force for the force that applies to this tine to return it back to the original placement is negative k times the amount of displacement. So if you think of, maybe I show it using the other tine, that is easier to uh, understand this. So I'm going to delete this, and I'm going to show it on the other tine. So imagine you apply force like this, and imagine this is the positive x-axis. So what happens is, you apply force like this, and then you release it, and then that means there is a force that is uh, corresponding or proportional to the amount of displacement in negative direction, because because you bend it outward, and then the force tries to return the tine back to its position. So that's why the negative sign here, which means counter the direction of plus x that you try to displace the tine. Now, we know that from Newton's second law, F is equal to mass times acceleration. So in this simplified system, what I can do is, I can say F is, according to Hooke's law, negative kx equal to m acceleration. Acceleration is nothing but the second derivative of displacement. Okay, so we have a second order differential equation in this system. Obviously, if you want to go with brute force approach, then you would say, okay, I have x of t that I'm trying to figure out, and the only information I know is, if you want to even further simplify this, you can do that. You can just say, okay, um, the second, maybe I write it this way. So you can say a second derivative of displacement, according to the equation we identified here, is equal to minus k over m times displacement. Displacement is a function of time. So you would say, okay, my guess is, looking at the signal x of t, since its second derivative is equal to or proportional to itself, that exactly reminds us of sinusoidal signal, sinusoidal cosine. So you can start from that guess, but one thing we can do is actually applying Laplace transform to this. So if we apply Laplace transform, so let's say we apply Laplace transform to both sides of this equation. So applying Laplace, we get s squared x of s, and then of course we get minus s x, or displacement at time t equal to 0, starting moment. Okay, and then we get minus the first derivative of x at time t equal to 0. So that would be x prime 0. And then equal to this constant minus k over m x. I mean, it should be capital S, because we are doing the Laplace transform of both sides. So we get x of s as well. Okay, so let's just shuffle things around to have a nice setup. So s2 plus k over m. I just moved this k over m from minus k over m x of s from the right side to the left side. So I guess s squared plus k over m times x of s is equal to, now let's move these components that are not function of s to the other side. So what you get is s x at time t equal to 0, that's x 0, and then plus x prime, the first derivative of x at time t equal to 0. That's what we are getting. These are, okay, so that's what we have. Now, let's just tidy up. So x of s is basically s x 0, and then plus x prime at time 0, divide by s squared plus k over m. Okay, nice. In this specific example, at time 0, when we sort of force out this time outward in the positive direction on our nominal x-axis, there is no speed because the first derivative of displacement is a speed or velocity. Velocity exactly at time 0 when we are about to release the time that is bended is 0. So we can assume that this component is 0. So our equation or the resulting Laplace transform numerator simplifies as s times x at time 0, which is a constant, divided by s to the power 2 over plus k over m. Okay, so now this is officially Laplace transform of a cosine, this one, this whole thing. Okay, so imagine if you don't remember that, one thing you can do, you can just use a very simple partial fraction expansion. So you can do, let's keep x0 outside because it's irrelevant to this conversation. It's a constant. Define x0 means displacement at time 0. How much you push this time outward, how much do you force it outward. So that's the initial displacement. And then denominator, what we can do is, this is effectively, this denominator, s squared plus k over m, is effectively equal to s plus j square root of k over m times s minus j square root of k over m. Okay, so we can just have s plus j um, square root of k over m, let's say alpha, we don't know what alpha is, plus beta s minus j square root of k over m. I mean, this is a redundant step in case you know you're comfortable that this s over s squared plus k over m is the Laplace transform of cosine. We are done. I am just doing this so that in case you want to see how we can arrive at that outcome, you're comfortable with it. Okay, in this case, what do we see? If you just shuffle things around here, simplify it, you get this outcome. X of s is equal to x0, and then you get exactly the denominator that you wanted, original denominator, which is obtained by product of these two. So you get s squared plus k over m. But in numerator, you get alpha plus beta s, okay, and you get alpha minus beta times j square root of k over m. You don't have this component in the original numerator. You have to get rid of it. So this indicates that sorry, indicates that alpha should be equal to beta so that this component goes away. And here, alpha plus beta has to be equal to 1 um, because we want the only thing remaining in numerator to be x of 0 times s, like what we have here. So from there we get alpha plus beta has to be equal to 1. So the outcome of this whole thing will be alpha should be equal to beta equal to uh, zero 0.5 or 1 over 2, however you want to however you like to write it. Okay, so this is what we wanted to get, and as a result of this outcome, what we can write is as simple as this now, that x of s is equal to x0 over 2. That's because alpha and beta are 0.5. And then we have 1 over s plus j square root of k over m, and then 1 over s minus j square root of k over m. Well, these are super simple. So if for these two components that are just first order in denominator um, of s, then when we do the Laplace inverse Laplace transform, we get from here x of t therefore has to be in the form of x0, which is a constant, divided by 2, and then inverse Laplace transform of this guy is just as simple as e to the minus j square root of k over m t, and for this one is as simple as e to the plus j square root of k over m times t. Okay, so that is the end of the story, because the sum of these two complex exponentials divided by 2 is just the cosine. So we get to the point that we can write x of t is equal to x0, or displacement at time 0, times cosine square root of k over m times t. So that's the governing equation, sinusoidal equation for this ideal tuning fork. And what we learned from this simple equation is amplitude, as expected in an ideal system that is not non-attenuating, is just the initial displacement x0, and omega, or the natural frequency of this system, is um, just square root of k over m radian per second. So what is this trying to tell us is not only we are able to use the Laplace transform to figure out and solve for this, but also at the same time it means that the k, which is the stiffness coefficient, uh, the stiffer this system is, or this tuning fork is, you end up with higher frequency oscillation. As you can see, the frequency of or radiant frequencies correspond, angular frequencies proportional to the square root of stiffness, and the higher the mass, as expected, result in lower frequency of oscillation for the mass of time. I'm referring to mass of each of these time. The higher it is, you will end up with lower frequency of oscillation, because the frequency of oscillation is inversely proportional to a square root of m. Okay, I hope that this is helpful in terms of just in a simple, simplified, idealistic mechanical system, how we can write a simple differential equation and how we can use Laplace transform to solve for expected natural frequency.